Good morning. Finally set up here. Perfect. So I just posted a formula sheet. Now we're online, right? Well, we're not online officially, but because so many of you are joining online, and we just decided it was, well, I decided it was easier for me to just have one mode of delivery, otherwise it gets crazy. The testing will be online. And we're just doing quizzes, and then the final exam will also be online, right? And so it'll be open book, because I'm not gonna even try to pretend to police you. That's crazy. And so it is open book. So I want you to start to develop your own formula sheet. Okay, but I just posted one on our Moodle page, and here it is. It's called formula sheet. It is from Stat 121, 124, because I haven't really taught this course in person, so I don't have one specifically for this course, and that's okay. But Stat 121 and 124, they cover the same stuff. It's just we go a little bit deeper into some of the later topics. Okay, so a lot of these formulas will apply for us as well. And then some. But it's nice to have like a jumping off point for you guys, at least if you're trying to make your own formula sheet, then at least you know kind of what you would have had in person. Okay, so it's just kind of to help guide you along, and I have broken it up into little sections. And so last day we started talking about probability, and that's kind of the first time that we start to really kind of need formulas for chapter 1 and 2. In our case, they rearranged the chapters, but so the chapter headings don't really make sense anymore, but you can figure it out. It's not until we get into probability that it's like, okay, there's a lot of kind of specific formulas here that we should keep track of. So as a review, I just want to go through some of the formulas that were covered in the video from Friday. Let's see here, where are we? There. So, before I do that, I want to mention that quiz number 1 is going to open on Friday. Friday at 8. Yes, I think I start at 8. Yeah, Friday at 8, and then it's going to close Sunday at 11:59. So anytime in that time period, make sure you carve out 50 minutes to do the quiz, and then probably another 10 minutes to upload your work. Okay. Yeah, so it is on our playlist. So I just add them to the playlist. And don't worry, we'll do a pretty thorough review, but yeah, it should be there. It's just called probability, or maybe it's even just called chapter 2. I can't remember what I said. I think. What did I do? Oh yeah, so defining probability, I told you to watch the first 51 minutes of the chapter 2. So the probability section used to be called chapter 2, but now it's chapter 3. It's the same material. Yeah, and then I posted the chapter 2, which is now chapter 3. The recording notes are here. But that's for that whole recording. So, I mean, if you wanted to just watch that instead of this, then that's fine. We're going to talk about the same stuff. So, in fact, that's exactly what I want to say now. So it's all deja vu. Okay, so it's there, and I just kind of tacked it on to our playlist. Okay, but I did only want you to watch the first 51 minutes. Ideally, I wanted you to watch the first hour and 17, but it felt like a big ask for a 50-minute class. So forget it. Okay, so quiz number 1. Quiz number 1 will be available from 8 o'clock on Friday until, 11. Oh, kind of using different notations here. Guess I should be consistent. Till 11:59. Man, I can't write at all today. On Sunday. So midnight, pretty well. Okay. 50-minute timed quiz. And with 10 minutes on top of that to submit your written work. With 10 minutes after that to submit your written work. That's just as a safeguard, right, to submit your written work, because it's just in case, you know, it's our first time doing a quiz, and what if your answers didn't get saved or something like that. It always happens to somebody, so I would hate for it to be you, and then your answers are all lost, and there's no way for me to give you any marks, right? So at least if you've submitted your work and you have kind of a record of the answers that you submitted, then I can give you marks retroactively. And so it's just a safeguard. It's not for marks. The written work, I might give you like one completion mark or something like that, just to kind of say, hey, you did it. But you have to submit your written work. Okay. Okay. Good. You watched the whole like 2 hours? Someone just messaged and said they watched the whole hour, or the whole, I think it's like 2.5 hours. Yeah. Yeah, we're just gonna keep going through that. So you're off the hook for the whole week. That's another way you could do it. You could just watch that video and then yeah, that's that's very, very hardcore. Yeah, that's great. Yeah, those videos are really long, but it is, you know, I did sit down and I recorded them and I said everything I wanted to say in those videos. So that is something that you can do. I can't believe you watched all, I think it's like 2.5 hours of probability. It's insane. I only meant for you to watch a little bit. Okay, so, but we are just going to keep going through that material. So let's do a little bit of review in case you haven't had a chance to watch the video yet, or the first 51 minutes at least. So a little bit of review. One really important thing that I want you to always kind of keep top of mind is the fact that a probability, or is a percent, or sorry, it's not a percentage, but it is a proportion, which is roughly a percentage. Okay, so all those 3 P's mean the same thing. So a probability is a proportion, which is roughly a percentage, right? Because we have to multiply by 100, and then, right, so times 100 gives us a percentage, but all those P's mean the same thing, okay? What gets confusing is chapter 3 is the only chapter that we call probability. Now, it's kind of a different kind of probability that we're looking at. We're going to look at a little bit of combinatorics, and if you did, I think it's in Math 12, where you do a little bit of combinatorics. So, you know, like card games and stuff like that. But we're not going to focus on that at all. Okay, so but it gets a little bit confusing. So the reason it's confusing is because we talk about probability later on, but we're not going to talk about it in the same way that we do in this chapter. Okay, so this chapter is the only one that's called probability, but then we talk about probability in a different sense throughout the rest of the course. So, and this section is the one that people dislike the most, and that's okay. That's just normal, because it can be really tricky, and even subtle changes in the wording make a huge difference. And so it's kind of like, it's really frustrating sometimes, but it's something we have to just work through, and it's going to be fine. Okay, so I guess the the summary of that is, we're not going to do this the whole term. It's just for this chapter, so just stick with it. It's fine. Okay, so questions in this chapter are going to ask you for what's the probability of this happening, or what proportion of animals have this happen, or what percentage of people feel this way, right? And so, but all of those questions, they're the same because these are all the same things, right? Probabilities, proportions, percentages, they're all the same. Okay, so how we solve the problem is the same for all of these. Okay, so I posted that formula sheet, and there are a couple of things there that I wanted to grab here. Okay. Oops. From the formula sheet posted on Moodle for reference only. Okay. Just because you can build your own formula sheet, I would encourage you to build it around this formula sheet, but if you kind of have your own flow, then that's great. Okay, so the first part of the formula sheet, and this is chapter 3 now, but that's okay. The first part of the formula sheet really just outlines some key properties of probabilities. So for example, probabilities have to be between 0 and 1, right? And so here, P of A, so we use this P of and then some event A. A is just shorthand for some outcome or some event, and the probability of that event has to be between 0 and 1, and that's a fact, right? And so even if you convert it to a percentage, right, you can only be between 0 and 100%, and so it stays the same regardless. And so here, let's start with P of A is between 0 and 1, right? So all probabilities must be between 0 and 1. All proportions have to be between 0 and 1. All percentages have to be between 0 and 100, right? And so, so that's just a fact to keep in mind. Okay? And then we said, so that was, I'll kind of link these up with colors here. We're trying to, P of S equals 1. What does that mean? S is a special character that we use to denote the sample space. And the sample space is the list of all possible outcomes. So if we consider all possible things that can happen, the probability of something of those events happening is 1, right? Something, if we roll a die, for example, 1 of the 6 sides has to come up. Right, so the probability of something happening from the sample space is 1. Okay, or once we consider all the possible outcomes, then it has to be 1. So the probability of the sample space, which is all possible outcomes, is 1, right? For example, if we roll a die, the probability of one of the 6 sides showing up is 1 or 100%, right? So if we roll a die, the probability of one side being face up, is 1 or 100%. There. Okay. So get. And then we talked about the complement, and I just can't help it but think of that song, Give Me Compliments. It's like a German song. Anyways, it's really funny and you should look it up, but it's spelled differently, but it's pretty funny. Let's use orange. Orange you glad. So we use A with a superscript C to denote the complement of A, which is basically it is all the events that are not in A. So sometimes I'll read this as not A, right? Or instead of saying the complement of A. So the complement of A is, well, let's just read it as the complement of A, which is everything not in A. And sometimes I'll read this as not A. Just to kind of simplify things a little bit. Okay. So if I tell you that regardless of what A is, if I tell you that the probability of A happening is 0.4, right? Then just our brain does a really good job of saying, okay, well then the probability of A not happening has to be 0.6, right? And why is that? Because we have to do 1 minus the probability of A happening, right? Because either A happened or A didn't happen, and that's our entire sample space, right? And so that's where we get this formula from, but our brains already know this formula, so we don't actually need it. But the probability of not A is 1 minus the probability of A. So the probability of the complement of A is 1 minus the probability of A, right? Since A and the complement of A must make up the sample space. Right? So we kind of go back to the sample space definition, which has a probability of what? 1, right? So, and that's where this 1 comes from. Okay. Somehow I got through a lot in 50 minutes, I think, because I also know I had time to introduce the general addition rule. So the general addition rule is kind of fun, interesting, whatever you want to call it. I'm not going to write it all in pink because it's like kind of my reserved color. Important things, fun things. But the general addition rule says that the probability of A or B, so in general, two events A or B, okay, is going to be the probability of A plus the probability of B. And then what we have to consider is the possibility of them happening together, right? So minus the probability of A and B. Yeah. The easiest way to think about this, and we use a deck of cards, right? Because a deck of cards, a card can be a face card, but it can also be, a diamond, right? And so I think we use face card and diamond in that example, right? And so there's that overlap there. So if we let A be the event that you draw a face card, and B the event of drawing a diamond, there are three cards that are both face cards and diamonds, right? So if we just considered adding up the probability of drawing a face card, right, which I'm pretty sure is what, 12? 4 times 3 is 12, right? So 12 out of 36. And then, because there are 36 possible, I think, no, 52. I don't know where I got 36 from. I do know 2 dice, but anyways, it doesn't matter. 12 out of 52 is the probability of drawing a face card. And then there's 13 diamonds, right? But then we have to subtract that overlap where they're both face cards and diamonds. Now, I don't want to redo that example, but I do want to show you in general, the easiest way to visualize two events happening at the same time is through a Venn diagram, right? And so we can draw a Venn diagram here like this. Okay. This outside rectangle is the sample space. Okay. So this rectangle here, let me see here. I'll just highlight it all. Put a little frame on here. This is the sample space. So all possible outcomes are wrapped up in this rectangle, and that's typical. That's how we show it. And then we say that, okay, I could have, some event A. So if we go back to the cards, and this is where people freak out. Oh, I don't know cards. I don't know, how many face cards and whatever. And I'll just tell you how many there are. It's okay. But I think we all understand, a deck of cards, there are some face cards, there's diamonds, there's hearts. I can only think of the red cards right now. That's okay. Right. And so there's 13 of each. And so there's some key components that we kind of keep track of. But in general, right, we understand cards. So if I draw some event A, right, usually I have a circle and I'll put an A here, and then I'll have some event B. And to show that they could potentially happen together, right, I show the overlap here, right? And so this overlap is A and B when they happen together, which we also call the intersection, right? So A and B is the shorthand notation or the set notation that we use. So this is the intersection. Oops. Intersection, which you read as and. Oops. Okay. And I kind of imagine, right, drawing a little line across. Sorry, it got a little faint there, but I draw a little line across, and that's what triggers my mind to say, okay, that's the and. And then the opposite is the union, which we read as or. I'm not going to keep that line there. But versus the union, which we read as or. Okay, so that's just set notation. Often I'll just use the words and or, but it's good for you to be familiar with it if you're reading some other textbook or something, right? So this overlap here, that's the intersection of A and B, and that's when A and B happen together. This is a good time to introduce the idea of two events being disjoint. Two events are disjoint if they can never happen at the same time, right? So it's a special case where the probability of A and B is 0, right? So it means that there's no overlap, there's no probability of them ever happening at the same time, right? And so here I'm going to introduce A and B are disjoint if they can never happen at the same time. Okay. Which means what? The probability of A and B is 0, right? And visually, it would look like this. You've got your sample space, you've got A, and then you've got B. Okay, but being disjoint is such a special case, and it's pretty rare, that it is something we need to be aware of. But most of the time, there will be some overlap here. And so that's what I want you to draw it as, right? And then it might come up that they don't share any space, and then you can redraw them as being separate, right? But often they will have some shared area. Okay, so going back to the Venn diagram here, the area of A is showing all the outcomes in A, and the area in B is showing all the outcomes in B. But it's also a way that we can show the probabilities, okay? Because the outcomes are also connected to the probabilities, right? And so if we think about these circles as being either the probabilities or the outcomes, it really doesn't matter. So we can write the number of outcomes, or we can write the probabilities, and we can use them in the same way, which once you get to using them, then that'll start to make more sense, right? And you'll see, oh, okay, I could use the counts, or I could use the probabilities. As long as I'm consistent, then it doesn't matter. Okay, so if I want the probability of A or B, well, if we look at this diagram, right, I want either in A, so I'm interested in they're either in A, or they're in B, or they're in both. Okay, so so for us in statistics, when we say A or B, it can be in A or B or both. Okay. In A or B or both. Oops. Okay, so visually what that looks like is everything that's in any of these areas here. Okay, so let me see here. If I can kind of trace around. Kind of looped a little high there, but that's the probability of A or B. Now, if we think about the circle of A being the probability of A, then if we want to find the area in these kind of, I don't know, eyeballs, right? Then if I take the probability of A, right, so here, plus the probability of B, then I've counted this overlap twice, and that's a problem, right? But we can easily fix that by kind of shaving it down to be on one level, and that's why we subtract the overlap. Yeah. And so we use this general addition rule a lot, okay? And often how we're going to use it is you'll have, from either previous questions that you've answered or just from the question itself, you'll have 3 of the 4 components and you'll have to solve for the 4th one. You're not always, and it's rare that actually you're solving for the probability of A or B explicitly, right? Usually you'd have to find the probability of A if you have these 3, for example, or B or A and B, that kind of thing. Okay, so given 3 of the 4 pieces of information, we usually are asked to solve for the 4th piece, right? Not just the probability of A or B, but we use the probability of A or B is the probability of A plus the probability of B minus the probability of A and B to solve for the 4th. Oops. Okay. So that's how those questions are going to go. Okay. So today, I want to keep going. There was a little bit that I didn't quite get to in the 50 minutes, which I had hoped, but that's okay. We need to talk about independent events. Okay, so we've talked about disjoint events where there's no shared outcomes. And so the probability of A and B must be 0, right? And so here I'll just highlight their disjoint, and maybe I should make it clear here that if they're disjoint, it means that they share no probability. The probability of them happening at the same time is 0, right? Which I guess I should emphasize, right? How does that affect the general addition rule? Well, if there is no overlap, then we don't need to subtract it because it doesn't exist, right? So then you're subtracting 0, right? So you're better off just using this general addition rule all the time. And then if you find that the probability of A and B is 0, then you can just plug in 0, right? Okay, let's talk about, so that's kind of the end of the review. Do a little twiddle thing. I don't know what it's called. I'm sure it's got a fancy name. So independent events are different from disjoint events in the sense that disjoint outcomes or disjoint events mean that they can never happen at the same time. So, and that affects the probability, but independent events has to do with the probabilities being affected by something happening already. So 2 events or outcomes are independent. And okay, this is where I kind of say, yes, there is a difference between events and outcomes. So an event is a set of outcomes, but let's just focus on events, right? Because it's pretty rare that we actually consider single outcomes. So if you want to, you can just ignore this. It's just being proper, okay? And just focus on calling them events. That's fine. So 2 events are independent if knowing the outcome of one does not affect the probability of the other. Okay, so if you're flipping a coin, even though it's human nature to start to think, well, I mean, I've flipped 3 heads in a row, the next one has to be tails. We also understand that the probability of heads is still 50-50, right? There's still a 0.5 probability of getting a head again, right? For a 4th time in the row, for a 5th time in the row. Right. And so the probability of that happening overall is very low, right? But it does happen because these are independent events. Okay, so if you roll a die, for example, same thing, the probability of getting a 6 is always the same, right? Assuming you have an even die. Okay, and so two events or outcomes are not independent if knowing the result of one affects the probability of the other. Okay, so some examples that we talk about are stocks, right? Which we understand they kind of rise and fall together, right? And so, if a stock went up yesterday, it's more likely to be going up today again. And then slowly, we get these up and down shifts. But in general, if we're looking day to day or hour to hour, right, then we see these trends. Weather, right? If it was snowing yesterday, it's more likely that it's going to snow today, right? Than not, right? That kind of thing. Disease, right? If your sibling is found to have some inheritable disease, then you are more likely to have that inheritable disease because the probability just increased, right? And then and cards too. So a lot of events are not independent, right? For some reason, we don't call them dependent events necessarily. We just say they're not independent. It's weird. You can call them dependent events, but for some reason we just don't. But if you're sitting with a hand of cards and you have 5 red cards, then you know that those 5 red cards are in your hand and they're no longer in the deck. Right? So that affects the probability of the deck cards being red, right? Now the probability of the deck cards being black is slightly higher than red, right? And so you have some outcomes that have already happened, your cards, right? And then that affects the probability of the others. And so those would be not independent events. And so, and I've got a little funny here. Where is it? So here, this is referring to independent events. Third times the charm, false. Each time has an equal probability of being the charm. That's true. They're independent events, assuming they're independent events, I guess. So anyways, so the independence is directly related to the probability of something happening. Okay, and so it does not affect, so if knowing the outcome of one does not affect the probability of the other. Okay, and so there are mathematical ways where we can check to see if 2 events are independent. And that's what I want to kind of talk about today. And where is it? I'm going to draw on this so it bumps it up. Okay. So what we say, well, so usually, so I got a direct message that is kind of saying, okay, well, so should we know about cards or no? You don't have to, right? I've given you, I think in the handout, there is a deck of cards that I've laid out in case you ever need it. So this is a deck of cards, right? And so, I mean, but I'm going to draw on basic knowledge, like how many face cards are there, right? How many suits are there? How many cards are there? 52. So, so not really, but I mean, it helps, I guess. Okay, so we can check to see if two events are independent mathematically. And that's how I want you to be checking it. So, we could argue whether two events are independent. Oh, well, because knowing one affects the probability of the other. That's fine. But I also want you to support it with a mathematical check. Okay, so the check here is if A and B are independent, and it's really important that we think about that. So if they're independent, then the probability of A and B happening together has to be the probability of A times the probability of B. Okay. So we can use this property to determine whether A and B are independent, right? So if we have to check to see if two things are independent, if A and B are independent, then what we check is, okay, if I have, it assumes that I have the probability of A and B, I have the probability of A, and I have the probability of B, then I can multiply the probability of A times the probability of B. And if they're not the same, then they're not independent, right? And so if we need to answer a question about whether two events are independent, you need to check it mathematically. So if we need to answer a question about whether A and B are independent, you must check it mathematically. Oops, there. Yeah. Okay, so so that's just good to keep in mind. And another kind of word of warning is this is only true. So this calculation only works if they're independent. Okay, and so a lot of people want to just kind of go ahead and use this to find the probability of A and B without knowing if they're independent or not, right? So if I've told you that these two things are independent, then yes, you may use this calculation. However, a lot of people will just want to multiply the two probabilities together to find the probability of A and B, and that's not necessarily true unless they're independent. Okay, so you have to be really careful. Okay, let's see here. I think I've got an example. Oh, and I talked about expected values too, but I'll leave that for last day. So we've got an example, and we're introduced to a math class of 30 students, 17 are boys and 13 are girls. And on a unit test, 4 boys and 5 girls made an A grade, so got an A. And if a student is chosen at random from the class, what's the probability of choosing a girl or choosing an A student? And what I want to do here is I want to show you 2 ways that you can solve this. So as long as one of the ways makes sense, then you're good to go. Okay, so first I just want to answer it just by the information that we have. And usually that's sufficient. But then I also want to show you with a Venn diagram and how you can solve these problems with a Venn diagram, because especially if you get into kind of more complicated questions, then it's nice to be able to lay it out and know how to solve it using a Venn diagram. But you can just solve it by reading it and answering the questions, and that's fine too. Okay, and so one of the things that can be overwhelming is we have more than 2 pieces of information here. But what I want to do is I want to boil it down to just 2 pieces of information. Okay, so I have a math class, so that's going to be my my sample space. And so n is 30. And so my sample size and my sample space are those 30 students. And 17 are boys and 13 are girls. So what I can do is, if I focus just on my Venn diagram, then I can make a circle to denote the girls, and then everything outside that circle would be the boys, right? And same thing with, if I make a circle for the A's, then everything outside that A circle is going to be not A's, right? There were students who wrote the test and they didn't get A's, that's okay. So if we let G denote, so I'm going to use a capital G to denote randomly selecting a girl. And I'm going to let A denote randomly selecting an A student. As long as you define what those shorthands are, then you're allowed to use them, and I encourage you to use them. Okay. Okay, so what we want to find is, what's the probability of choosing a girl? So the probability of choosing a girl is, well, there are 13 girls out of 30, and that's the probability. I am not going to convert these to decimals. You can, and a lot of questions will ask you to, but I'm going to keep the exact values for now, because I can just tell that they're going to be irrational numbers and I don't want to deal with that. Okay. So then the probability of G is 13 over 30, and the probability of choosing an A student, well, how many A students were there? 4 boys and 5 girls. Right, so there were a total of 9 A students. So 9 out of 30 got an A. Okay. So what can I do? What can I do? What can we do when we live in a shoe? Well, I can have my sample space, which has 30 students, right? And those 30 students can be divvied up, and they can be divvied up into either girls or A students. So everything outside the G circle, those are all the boys. Everything outside the A circle, those are all the non-A students. And then here, this overlap is where I have G and A. So these are all the girls that also got A's. Okay. So from the question, I see that this overlap of G and A has a count of what? There were 5 girls that also got an A. Oops. So what I'm going to do is I'm going to, oops. Oh my gosh. Try again. There. I'm going to fill that with a 5. Okay. So what I'm going to do is I'm going to fill all of these components with the different counts, because that's going to help me answer the questions later. Sometimes it's helpful. Sometimes it's just nice to visualize it, but I just want to give you the tools so you know how to use a Venn diagram. But we have, notice that we have answered the question already. So if you're comfortable with just answering the question, that's great. I'm happy with that. Okay, I just want to give you another tool that you can use. Okay, so we know that there are 13 girls total, which means that the G circle has to have a total of 13, right? And so, but I've already used 5 of them for the A students, right? So 13 minus 5 is 8. So then here, I have 8 girls that did not get A's. Mhm. And what I had 4 boys that got an A, but the boys aren't girls. And so here I have 4. Okay. And then I have a total of 17 boys, but 4 of them, right, have already been counted here in this kind of half moon, I call it often. And so 17 minus 4 is, what color haven't I used? Maybe a dark or use pink. Right, so then 13 boys did not get A's, right? And so here I just want to highlight that this 4 is for this kind of half moon. So if you send me a question about Venn diagrams, I'll often talk about the half moon. So that's why I want to kind of highlight it. And then the middle section. So what you can confirm then is that all of these components have to add to 30, right? So if I do, I'm going to use my calculator here. If I do 8 plus 5 plus 4 plus 13, I get 30, right? And that's good. Right. Okay, so what's the next? Next thing I want to solve is, and maybe I'll grab the cute little image. I had to include it. I stole it from some textbook a long time ago, and I just think it's so cute. Anyways, doesn't matter. What's the probability of choosing a girl who got an A on the test? So now, right, I can look at my Venn diagram and I can see almost immediately that, okay, I need to choose a girl. So that means I have to be in the girl circle, but I also need to be an A student. So means I have to also be in the A student circle. And there's only 5 of them there. So 5 out of 30, or if you prefer to just get that information from the text, then that's fine, right? From the question, that's totally fine. Either way, the answer is 5 out of 30. Now, the key is how we denote that. We're going to use probability notation, right? So the probability of G and A is 5 out of 30. Right? Which we can see from the Venn diagram or just the question. Either way, that's the answer. Oops. So here's where it gets a little dicey, right? I guess I shouldn't say dicey. Dice questions, no. The difference between the wording here is subtle, right? But it's something that we have to pay attention to. Let me bump it over so it looks kind of lined up. Here, we wanted to know the probability of choosing a girl who got an A on the test. But now we want to know what's the probability of choosing a girl or an A student. Okay. And so I can use the formula because this is the same as asking for the probability of girl or A, right? Which we have seen a formula for. So we have a formula and it turns out we have all the different components. That's how these questions are going to go, right? You're going to have the components from before, and then you're going to use them to solve this next problem. But we could also use the Venn diagram, right? And we can kind of get there the same way, because if we're looking at a girl or an A student, remember the or for us is going to be, it's always going to be G or A or both. Okay, and that throws people off sometimes, but it's G or A or both. So then if I'm in G and only G, then that's 8, right? And if I'm in A and only A, then that's +4, right? And then the last option is or both, which is +5, right? So I could use just the Venn diagram and I could say 8 + 5 + 4. Those are the areas that satisfy this question. And so that's the number that I want out of 30. Or I can use the formula, right? And so here I'll say from the Venn diagram, we have 8 + 5 + 4 out of 30, which is what? 8 + 5 + 4, which is 17 out of 30. Or we use so many different ors here, or we can use the formula, right? The general addition rule, which says the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. This is one of those scenarios where you have 3 of the 4 components and you have to solve for the 4th one. Sometimes it takes a little bit of concentration, right? Because the G is going to map to the A, right? And so wherever I see an A, I'm going to mentally replace it with a G, right? Because the A is just a placeholder for some event, right? It gets confusing because we also have an A here, but what I'm going to do, and just to kind of emphasize that that's what we need to do here, wherever I see a B in the general formula, I'm going to replace it with the event of an A student. Okay. So you need to really keep track of things, but wherever you see a B in the general formula, you're going to replace it with an A student, which gets confusing. The reason I don't want you to all of a sudden switch things around and may write A or G is because sometimes, not often, but sometimes the order matters. And so here, because we're asking for the probability of choosing a girl or an A student, I really want you to keep that same order. Okay. You can check both. If it doesn't matter, then you can rewrite them, but then you've solved it twice and what a waste of time. So what we have then is we have the probability of G or A is the probability of G plus the probability of A minus the probability of G and A. Kind of glitching out. It's because I think it's because it's a page break there, but that's okay. Okay, so now I have all these components, right? Because we all have already been asked to solve for the probability of G, the probability of A, as well as the probability of G and A. So I have the probability of G is 13 over 30. I have the probability of A, which is 9 over 30. Right? Minus the overlap, which we were just asked to find, which we said was 5 over 30. Now, if you had used rounded values here, I would encourage you to keep at least 4 decimal places. But in this case, because we're adding and subtracting fractions and we have a common denominator, that's safe, right? We should, be comfortable with fractions. So a common denominator of 30 means I can just add and subtract the numerators. And so I get 13 plus 9 minus 5 over 30. Okay. Which puts me at 13 plus 9 minus 5 is, again, 17 over 30. Which is the exact same answer that we found from the Venn diagram, right? And so that's what I mean. So sometimes the Venn diagram is more work, sometimes the formula is more work, and you just have to pick one that suits you, right? So pick one that works as long as you're landing on the same answer. I don't personally care how you got there. Okay. I prefer the formulas most of the time. But usually I'll use both just to kind of check myself and make sure that I'm getting the same answer, right? So I encourage you to do the same. Okay. So the last question we're going to answer here is, are choosing a girl and choosing an A student independent, right? So are these two events independent of each other? Only one way to find out, right? I don't want you to really sit here and philosophize for too long whether they're independent or not, because we have a mathematical formula that we can use to check it, right? And so what we need to do is we need to check if the probability of A and B, is it equal to, and so I'm going to denote that by putting a little question mark over the equal to sign because I don't actually know, is it equal to the probability of A times the probability of B? And of course, for us, again, I'm going to use that mapping technique where, okay, the first event, the general event, is denoted by an A, which is choosing a girl in this case, right? And so here I'm going to rewrite this as the probability of G and an A student is it equal to the probability of a G, so probability of a girl times the probability of an A student. We have these values, right? And so we can plug them in and we can actually check it to see if they're the same or not. Okay. So, because I have it here, and from a previous part, right, we know the probability of G and A is 5 over 30. You can convert these to decimals, but then I want you to keep all your decimal places until the very end. Because even if the answers are very close, they have to be the exact same, right, to be equal. So we have 5 over 30. So I'm going to keep using the fractions, the proper fractions. And so 5 over 30, is it equal to, so I'm still not sure, is it equal to the probability of G, just kind of going back here, was 13 over 30. And then I also have the probability of A, which is 9 over 30. 13 over 30 times 9 over 30. Multiplying fractions, I can just multiply across, right? And my fun calculator actually goes ahead and reduces the fraction to the smallest possible denominator. So if I go 13 over 30 times 9 over 30, it just jumps straight to 13 over 100. So it's reduced it and done some fun things, right? Is that equal to 5 over 30? It doesn't look like it, right? Just because 13 over 100 is reduced. But what I can do is I can check it with just converting to decimal places. So 5 divided by 30 is 0.1666, repeating. is that equal to 13 over 100? Oops, not 1,000, 100, which is 0.13. It's not. Remember, they have to be exactly equal, otherwise it's not true. So then I'm going to say not equal to, right? And here I'm also going to make a note. These values would need to be exactly equal. Okay, which they're not even close. I mean, you could think that they're pretty close, but it doesn't matter, right? They have to be exactly equal. So then our argument is no, these are not, right? To answer the question, are choosing a girl and choosing an A student independent? No, they're not independent, because the probability of G and A is not the same as the probability of G times the probability of A. So no, let's say G and A, I'm just going to use the shorthand. G and A are not independent since the probability of G and A does not equal the probability of G times the probability of A. And sometimes I'll even show off and use the values, right? Since 0.1666 repeating is not the same as 0.13, but that's okay. Okay. It looks to me like I was a little ambitious in finishing chapter 3 before the quiz, but maybe what I'll do, because starting conditional probability, I guess we could start conditional probability, but we'll just have the quiz go up to conditional probability, right? So we'll keep going through conditional probability next day, but I'll start it and then can keep going, but I meant to have all of chapter 3. Hey, why is it not picking up? But that's okay. It's the meat and potatoes. And this is 3.2. Okay. So here, quiz number 1 will go up to and including this section, right? Which we will continue next day. I just want to introduce the idea of conditional probability, and then we can kind of jump in on Thursday, because I do want it on the quiz. But what you're going to find is that I did sneak some of these questions on an assignment already, and I'll post a probability assignment for you guys. But you've already had to kind of wade through conditional probability questions without calling them that, so that's okay. Okay, so we've already seen contingency tables, right? And that's where I made you kind of practice this idea of conditional probabilities. And they kind of look like 2x2 tables or more, but we're going to focus on 2x2 tables. And often we put the totals in the margins, and we can convert these to probabilities, and we can do all kinds of fun things. But now we're going to use these values to answer probability questions. So we're looking at a sample of 792 teens, and we have asked these teens through a survey probably are you going to college immediately after high school? Yes or no, right? And so the college variable means that the teen went to college immediately after high school. So it kind of, it doesn't matter if you went to college 2 years later, a year later, or whatever, it's immediately after high school. So it's very specific. And then they also asked, okay, well, do you have at least one parent at home with a college degree? So then the degree variable indicates whether at least one parent of the teenager completed a college degree. Now, what I want you guys to think about is, what would this data set look like, right? So you would have a student, right? And this is just something that I want you to start thinking about. Okay, how would this data set, what would it look like originally? So here we have it summarized as a table, right? But it's good to know, because if we can see this table and know what the data would look like behind there, then if we're faced with the problem of, okay, I have this data, what do I do to summarize it? Then if you see something like that, then you think, okay, I could summarize it with a table, right? And so what would this data set look like? You would have your data set, oops, it's not writing properly. It's so weird. Sometimes my Apple Pencil acts like it's running out of ink. It makes no sense. It's all electric. But anyways, so your data set would look something like this, right? You'd have student number 1, number 2, number 3, all the way up to 792, right? Because we took a sample of 792 teens. And then what would it look like? Well, I would have a college variable, right? And so here the name of the variable is up top, and the other variable that we've considered is the degree variable. Now, college variable is either a yes or no answer. Did you go to college immediately after high school or no? Right? And so maybe this one did, denoted by a 1. Maybe this one didn't. Maybe this one did. Maybe this one didn't. I don't know, just making it up. Right? And so it would be a series of zeros and ones, right? Either they did or they didn't. And again, the degree variable, right? Did at least one of your parents complete a college degree? Yes or no, right? So as soon as we have these yes or no answers, we're going to denote those by zeros and ones, and we call those binary variables. And so a degree, so maybe 0, 0, 1, 1. So now I have all these possible options, right? I could have a student who went to college right away after high school, but they didn't have a parent with a college degree at home. So those would be one of the people of these. Let's have a look here. So they went to college right away, but one of their parents does not, or not, none of their parents have a college degree. So they would make up one of these 214 kids, right? And so, so then everyone would be kind of divvied up into one of these 4 groups, right? Based off of these 2 binary variables, right? And so I'm just going to make a note here because I've said it a couple of times, and just in case. So these are what we call binary variables. And we're going to talk more about binary variables, but it's nice to have a little kind of, what would it look like? Okay. So same thing as before, we've established this shorthand of D means at least one parent has a college degree, and C means that the teen went to college immediately after high school. Okay. And I am all out of time to start something, but what I want you to do for next day is just think about how would you solve these problems, right? So, and of course, the answers are in the notes that are posted on Moodle. So it's not, hidden or anything. But that's what we're going to work through to talk about conditional probability. Right? If you have any questions, let me know. But otherwise, we'll pick up there on Thursday, and see you then. Stop this recording. Oh yeah, so are the class notes sufficient for the quiz? Yes, but I am also assuming that you're reading the textbook, but the notes are very close to the textbook. So I'm assuming you're reading the textbook, but yes, most of the quiz questions are from the class notes and the assignments.